All right, everybody, let's go ahead and get started here. My name is Martin Besner, and I'm the president and CTO at Staties. I want to thank you all for joining us in today's webinar, which is titled Design Evaluation. So tools for assessing your DOE quality. I think this is this has been a very highly requested webinar. It's also a topic that I think gets very little attention relative to the impact it could have on your own DOE work. So we decided that we'll try to do a 45-minute webinar about this and hopefully give you some information and practical advice that you can take and use in your own work going forward. Just some housekeeping things. We do have a pretty decent sized group today. So to prevent any audio disruptions, unfortunately, everyone is muted. If you do have any questions, you can go ahead and use that question feature in the GoToWebinar little widget. I try to check the questions every 5 to 10 minutes or so, or between sections. If if I don't end up getting to it, I'll try to send a reply via email, but you can also feel free to reach out to us at stathelp@staties.com. Okay, at this email address here. This email goes to our entire team of statistical consultants. So as you can tell right now, I'm not working on my email. I don't even have it open. So if you send me something now, I can't get to it. But if you send it to stathelp@staties.com, whoever's available first will jump right on it and get back to you. And as always, we will have the slides available on our website, and we'll also post a recording of this to YouTube, as well as I believe we still post them to our website, but it'll definitely be on our YouTube channel. So if you need to leave early or you'd like to hear an explanation a second time, you can go ahead and watch it as many times as you want. Before we get into the meat of the presentation, I did just want to point out that this summer, I see some names here who have taken our training before. We do have a new series of workshops, which is called Essentials, and these are basically 2 half days of training. Usually our workshops would be 4 to 5 half days of training, but we've gotten a lot more requests for shorter, quicker, more targeted training. So I encourage you to check this out. If you see something that you like today, probably the Essentials 1 or the Essentials 2 course, or even the Essentials 3 are going to talk about, they're going to hit a little bit on the points that I'm discussing today. So if you like more in-depth explanations and some software tutorials and hands-on learning, then you can feel free to check out our Essentials series on our website. So it's right here, staties.com/training/workshops. And now that we got that out of the way, let's see, what are we going to be talking about today? So as I was putting together this presentation, I realized that 45 minutes is unfortunately nowhere near enough to do justice to this topic. I mean, when we do our workshops, we spend probably half a day on evaluating factorial designs and half a day on evaluating response surface designs. And then if you take our mixture workshop, we spend at least a few hours. So to try to condense that all into 45 minutes is really, really difficult. So I'm going to just try to focus on the key points here. We're going to split this up into 2 categories. We're going to look at factorial designs, and we're going to look at RSM designs separately because they're not evaluated in quite the same way. And the 2 things the 3 things I'm really going to be focusing on is power, and give you a lot of practical suggestions and an example as well. Aliasing, we'll touch on that briefly. And then this thing that we call the fraction of design space, okay, which is used in response surface design. So that's used to evaluate response surface designs. And then finally, I kind of like to throw in all of the tips and tricks that I've collected over the last decade into a single slide, and hopefully this will be useful to you when you go off on your own. Okay, So first we'll talk about why do we even care about design evaluation? I mean, why are we even here today? Okay, so what's the motivation behind this? Why is it useful? And so on. So we'll start with this. A typical DOE, design of experiments workflow, usually looks something like this. I mean, and this is not set in stone. There are some iterations and alterations of this that are available, but typically the first thing you would do is you choose your fact. So you start with the problem, you choose the factors, meaning what is it that you're going to vary in your experiment, and you define the ranges, meaning, okay, across what range do you want to look at your factors? The next thing is that typically you use software to generate an experimental design that's based off of these factors and ranges, and hopefully it's capable of answering the question that you have. Evaluate, so once you generate the experimental design, make sure that it's adequate, make sure it's capable of answering the questions that you have, and that it doesn't suffer from any major issues. Finally, go ahead and actually perform the experiment out in the lab or in the field or wherever. Once you've got your data, fit the model, optimize, and then draw any conclusions about, well, we think the optimum is here. Maybe we weren't able to find the optimum, but if we tweak this, maybe we will be able to, and so on. And then finish or make changes and experiment again. Okay, so you might be done or you might need to keep working on the DOE. So we're going to focus pretty much specifically on number 3 today. We're not really going to do any data analysis. We're not going to do any optimization. We're just going to focus on setting up the design and evaluating it. Now, in my experience, this step here, which is highlighted in red, in my experience, I've been doing this for probably close to 12 years now on a daily basis in dozens of different fields, and with people in academia, working in industry, working as researchers. This is almost always skipped. Many cases, people will just generate the design and then perform the experiment. They won't look at it. And this, I think, is especially true in response surface and mixture experiments. Why is this? Well, I think, with factorial designs, most people are somewhat familiar with the idea of power, so they could kind of roughly see, well, okay, is everything okay? However, it's a little trickier, I think, in response surface and mixture experiments. So we're going to spend half of this presentation just on RSM design. So in my opinion, performing an experiment without evaluating it first is like, well, it's like buying a new car without taking it out for a test drive. You could say it's like marrying somebody without dating them first. I mean, it might work out sometimes, but a lot of times it's probably not going to. Or going to Costco and buying a pallet of something in bulk without first trying a very small sample of it. So, and so on. So you hopefully get the picture. And I'm not talking about even doing a really rigorous statistical evaluation here. I'm talking about just sometimes what I've seen people do is they'll generate the experimental design and then they literally won't even look at it. They'll just send it off to their lab tech to do the experiment. And they don't even look through all the runs, kind of scan the runs, see if there's any suspicious runs or issues that might crop up. So this is why we want to encourage you to be careful when possible. So with that said, evaluating a design means examining its properties before performing the experiment. So some of the things we might want to look for is like high power. Can we detect what we are looking for? Like if we're looking to see if temperature has an effect on your process, I mean, is the design that we're using even capable of answering that question? Good predictive precision. So in other words, if we're fitting like a response surface, I mean, how precise is that surface going to be? Like if we repeat the experiment, are we going to get a surface that's similar to the first one? Or are we going to get something that's wildly different? And finally, we want a design that can provide the information we need. So if we're looking for stuff like interaction effects, or if we're looking to fit a really complicated higher order polynomial RSM, we want to make sure that our design is actually even mathematically capable of handling that situation. This can save you from making very, very costly mistakes. In my 10 plus years of experience, a lot of quote unquote poor DOE results could have been avoided by evaluating an experimental design before doing the experiment. So I've seen people set up experiments where everything is aliased with everything else, and then they ask me, they say, oh, why can't I get interaction effects from this? I used up all my run budget. How do I get interaction effects? And we tell them, well, I mean, you unfortunately should have thought of that beforehand and set the design up to capture those. So, and when in doubt, I mean, ask a statistician, ask somebody to do a sanity check on this. And as I said, in this webinar, we're going to work through two major categories of design. So we're going to look at factorial designs here, okay? And we're going to look at RSM and mixture designs. So let's not waste too much time here, and we'll just get right into the factorial design evaluation slides. So just a reminder, for this is a one slide reminder. A factorial experiment, you have k factors. So a factor is something that we're changing as part of the experiment. And a factorial experiment, typically you would only look at like two levels of it, like a low and a high, like a low temperature, a high temperature. Or you look at, washer A versus washer B, or two different types of, material A versus material B, and so on. But typically, historically, they've always been labeled as a low level and the high level. And of course, you have at least one output response that you're measuring at each combination of the factors in the experiment. Now, the goal in a factorial experiment, and this differs from response surface and mixture experiments, is for you to be able to figure out whether any of the k factors, so that means as you go from the low to the high of any of the factors, is it impacting the response in a significant way? Meaning if you change the temperature from low to high and keep everything else constant, are you going to see a quote unquote significant difference in the response that you're measuring? So here are the things. Here's kind of a checklist that I like to give. How can we evaluate a factorial design before performing the experiment? So unfortunately, like I said, with only 30 minutes or so remaining, we can't go through every single one of these, but this is something for you to think about. And then I already talked about the first one. If going from low to high of a factor significantly impacts the response, meaning if there's an actual effect there in your process, is the experiment able to detect this with a high probability? Okay. So if temperature really does affect your process, and you do this experiment, are you going to be able to actually detect that? Meaning, is the p-value going to be less than 0.05? Or what is the chance that the p is it going to be less than 0.05 with high probability? Is aliasing an issue? So with the factorial design, a lot of times in smaller factorial designs, you'll do every single combination of runs, and aliasing, you never even need to think about aliasing. But sometimes people have 10 factors and they can't do 1,000 plus combinations at the low of all 1,000 plus combinations. They need to do a small fraction of them. And unfortunately, you lose some information there in the sense that you can't estimate everything independently of one another. So that's what aliasing is. Okay, you need to at least take a look at that. Is the design fully randomized? Sometimes what I'll do is I'll see people create an experimental design, and then they'll sort it so it's convenient, and then they'll batch things, and then they'll group things together, and then they'll split it all up. And they're essentially not, how should I explain this? But it's no longer a factorial design. They're basically doing like a split plot design, but not analyzing it as a split plot design. Now, Design Expert and Statis 360 are two software packages, automatically randomize everything. So if you just go do run number 1 all the way through the end, you shouldn't have any issues there. Sometimes, a lot of people ask, do I have enough runs? But sometimes, is the design possibly too large? Or can the runs be distributed in a better way? Now, do we think blocking might be necessary? What about center points? Sometimes people like to say, well, I have, a low and a high, but I want to test everything in the middle to see if there's any curvature. So these are all, I would at least spend, a minute or two on each of these points before actually performing whatever factorial design it is that I generate. Okay, we're going to focus mostly on power and answering this first question. We'll talk a little bit about aliasing in the next section. Randomization's pretty easy. It's pretty rare we run into designs that are too large, and if you have a design that's too large, generally it's not going to be a problem. It might just be using excessive resources. Blocking, unfortunately, we don't have enough time. We'll touch. There is an example that uses this, but and then finally, center points is something that you need to decide. So I think the best way to illustrate these things is to use a simple example. Now, when I looked at the list of attendees, we have people from a dozen different industries here. So just to keep things simple, I'm going to use a cake baking example rather than something like a polymer coating or something that not everybody's going to understand. So a team is baking cakes and is interested in figuring out how 3 factors affect the overall taste of the cake. So they have a bunch of stuff that's set as part of the cake preparation, but they want to tweak 3 things and see if they can maybe improve the taste by tweaking these 3 remaining factors. So got temperature from 350 to 400 degrees. Time in the oven, so 25 minutes or 30 minutes. And finally, the amount of milk they put in, 2 cups or 2.5 cups. Now, of course, you could say yes, they could test the center point here, but I don't think that was the issue there. So now the key is that each cake is going to be independently prepared and baked in the oven by itself. After you bake one cake, the oven's going to be cooled down and then it's going to be reheated between each cake. So we're basically trying to make each run as independent from the previous run and the future run, each future run as possible. Okay, we're not putting 4 cakes in the oven at the same time. We're not making a big batch of cake batter and so on. It's all independent. After the cakes are all prepared and cooled down, and I think they even put them in the fridge for a day or something. I don't remember all the details of this, but they are then rated on a scale of 1 to 9 by a panel of taste testers. So some questions here. How many cakes do we need to bake? I mean, there's 3 factors. Each have 2 levels, so there's a total of 2 to the 3 or 8 combinations. Okay. What experimental design should we use? And then what should we check before performing the experiment? So this example, I'm actually going to go through in the software, just so you can see, if you've never set this up before, just so you can see how to do this. So, excuse me while I switch to the software here. I'm going to click on New Design, and I'm going to start with the 2 to the 3 factorial design here. And I'm going to go ahead and click Next, and I need to type, let me make this text just a little bit bigger here. I need to type in my factor information, so I'm going to just to keep things short, temp, degrees Fahrenheit, that's 350 and 400. Time, minutes, 25 and 30. The milk in cups, that's 2 and 2.5. Okay, let me just make sure I got everything here. So that was this step and that was this step. We got those done. All right, and then we come to this page here. This is probably one of the more, this is probably, if you're going to evaluate one thing as part of this experiment, this is what you should do. This is the power page. Question is how many of you have simply clicked on the next button without actually paying attention to what was going on here? Okay, it's a rhetorical question. You don't need to admit, don't need to say anything, but the answer in my experience is that it's usually a pretty high number of people that are that are doing this. And notice that if you just do click the next button, you get a bunch of red text here, which should be hopefully set off alarm bells. So as I said before, this is the design power here. The screen, okay, yeah, deals with power, which is a critical statistic in setting up and evaluating factorial designs. Now, power is all about managing expectations. What effects is the experiment able to detect? Okay. So this is probably the most important statistic, and it's really going to be the only one we talk about today. And we're going to give a lot of practical advice on this in just a second here. But there's really 2 issues here. There's 2 things that you need to come up with before we can calculate power. Okay. So before you even do the experiment, when you're looking for changes in your response, meaning, okay, if I take factor A from low to high, what change in the response am I interested in? Like if I have a yield, a chemical reaction, and I say, well, if I can get my yield to go from 60% to 60.00001%, am I going to be happy with that? Probably not. Okay, same thing with like with this cake example. If I'm able to go from a rating of 6 to 6.00001 by simply tweaking the temperature, is that something that I'm going to care about? The answer is no. Okay, so what you want to think about is what's kind of the smallest change that you're interested in. Like on a 9-point scale, maybe a full point might be the smallest thing that I'm interested in, because maybe not many people could discern between a 6 and a 6.5, but people can tell the difference between a 6 and a 7. Finally, the noise in the process, the sigma, meaning how noisy is your process. So we should think that intuitively, bigger delta are easier to detect, meaning if I'm looking to see what takes my cake from a 1 to a 9, that should be easier to discover than what takes my cake from a 7 to a 7.1. Okay? And obviously, I mean, intuitively, it makes sense that if I have a process that's not noisy, that has good resolution, it should also be easier to detect active effects. So this is the quadrant of power here. Okay. This is what I like to show people because I think it shows power pretty clearly. So let's just say you have one factor, and I'm going to call this factor A. And this factor can take two levels. It can take a low level, which I'm going to call A minus, and a high level, which I'm going to call A plus. Okay, so this is here. I should have probably put this as A minus. This is A plus. Okay, so here is a situation where I have a very large delta, meaning if I go from the low to the high level of A, I get a pretty big jump in the response. And notice how there are multiple points plotted here because these are replicates. So notice here how like I don't even have to really have a statistical education here to tell you that, well, this is a very precise process. There's not much noise here in these replicates. So the chance that this gap occurred totally by random chance, I mean, it's like basically zero. So this is an example where you have a large delta, meaning you have a very strong effect and you have a very precise process. So it should be very easy in your experiment to figure out that going from the low to the high value of A does impact the response. In this corner over here, we have a situation where we have a very precise process, but the difference when you go from A minus to A plus, the low to the high level, is fairly small. But you know what? Because the noise looks like it's fairly low, I mean, to me, it seems like there's definitely a trend here. It seems like, you know, the chance that you get 5 points that are clustered here and 5 points that are clustered here by random chance, to me seems pretty low. So it looks to me like even if you have a small delta in your process, as long as the noise is small, you might still be able to detect it. Now here's an example. In this corner over here, we have a large delta, meaning when you go from A low to high of A, you get a big, you could see that this red and blue line, the red and the blue lines are the averages of the points here. So you could see that these red and blue lines are far enough apart, but you could also see now that you have a much more noisy process here, okay? So you have a lot of noise here, but because there's a fairly big gap here, you should probably be able to detect this change here. I think it's probably fairly straightforward. Even though you have a noisy process, because going from low to high produces a big change in the average, you should still probably be able to detect that. Now this one here is the most difficult case, is when you have a small delta, meaning you have a very small effect, but you also have a very noisy process. So notice how here the red and the blue lines are very close to one another. And I actually don't think that they're quite correct. It looks like they should be up here a little bit, but you should hopefully get the point that here I have a very noisy process, and it doesn't look like there's, you know, the trend when you, it's not very obvious that you see a trend. And it turns out that, for example, if like this point happened to by random chance be down here, the trend would actually look negative. Okay, so this is a case where it's actually very difficult to detect a change, and you probably need a ton of runs to really see a clear trend here, to actually be able to detect that change. So power is if you are going from the low to a high level of a factor, if going from the low to a high level of a factor really does produce a response difference of delta and the noise process in the process is sigma, then power is the probability of detecting that change. We generally want power. I think our rule of thumb is it's usually we want it to be about at least 80%. Otherwise, there's a good chance your experiment's not going to detect anything. And we typically only look at main effects for power. We don't usually really consider interactions. Now, in this cake example, what they were interested in is detecting differences of at least 1 point on a 9-point scale, and they thought that the noise was sigma equals to 0.5, which gives a signal to noise ratio of 2. So I'm going to go back to the software and actually type in this response is taste on a 1 to 9 scale, and the difference we want to detect is 1, and the standard deviation is 0.5. So power doesn't change because it's the same signal to noise ratio. Okay, so what we can do, and we'll talk about in just the next slide, is how to increase power. Is what we can do is we can go back to the beginning, take replicates up to 2, meaning we're going to do each of the 8 runs twice, and just see if that changes power. And it does. Adding a second replicate takes it up to almost 96%. So here's the question everybody always asks. If power comes in low, how can we increase it? Well, for one, add more runs to the design. Okay, more runs means more data, more information, should be easier to detect changes. As we saw in that quadrant of power, less noise means it's easier to see changes. Now, this doesn't mean simply choosing a lower sigma and plugging it in, but you actually have to make an effort to lower the noise. So maybe trying to calibrate your tools or equipment better. Sometimes repeated measurements might, averaging a bunch of repeated measurements might work. Sometimes blocking might be useful as well. Okay, those all tend to lower sigma. You could also choose a higher cutoff. Everybody uses the P of 0.05 as the cutoff for significant or not. And there's no law that says that you have to use 0.05. You could use a threshold of like 0.1. That means it's going to be easier to declare something significant, which means it's going to be easier to detect it as active. Of course, you don't get anything for free in statistics. This will likely cause more false alarms. You could also just simply choose a larger delta. It's not going to change anything, but it's mostly just about just lowering your expectations. Now remember, power is all about managing expectations. If the power isn't high and there's absolutely, like if you have a power of 60% and there's absolutely nothing you can do to get it up higher, you've tried everything, you have no more budget, you can still perform the experiment and hope for the best. Just don't be shocked if you end up with some missed effects. So this slide here basically just goes through what I showed you in the software when we added a second replicate here. So if you want to recreate this on your own, you can just follow these steps here. Now, other issues. Power is probably the most important statistic to evaluate before performing an experiment, but there are other things as well. If you actually build the design and go to our software and click on evaluation, here is where you're able to get all of the statistics that you want. So typically we select the main effects model, though that's typically what we evaluate at the first stage. And then you can click on results and you can see everything here. You can see the expected standard errors, the VIFs, the partial R-squareds, power, degrees of freedom, and core. You could see everything here. Okay. And this is literally that same exact slide the same exact screen that I had shown in our software. Now, what do these mean? Now, to be blunt, a lot of these are not super relevant, especially for factorial designs. Power is already defined and it's actually carried over from the design build. So you're going to see the exact same numbers as you did when you were building the design. We always get questions, well, what's this VIF, variance inflation factor? Well, a variance inflation factor is If you're not able to do full replicates of the design, and your design is not balanced, meaning each run is done the same number of times, you might get some extra error that's introduced, okay, due to the factorial design being unbalanced if you do like a partial replicate. And a lot of times there's nothing you can do about it. If you can only do 2 extra runs here, I mean, you just have to accept it. The degrees of freedom will tell you, for example, how many these degrees of freedom will appear right on the ANOVA table, and this basically tells you how much information you can extract from the data. And finally, the correlation matrix will tell you how, I mean, as the title says, how correlated the coefficient estimates will be here. Because we have a fully balanced orthogonal design, everything is white. There's nothing is correlated here. Again, generally, there are many times where you can't really control this. And sometimes some correlation in the estimates is not bad. I mean, adding an extra 2 runs is definitely going to outweigh whatever minor inconveniences you might see in the evaluation. Now, what about sigma? This is, I mean, this is probably, if I absolutely had to say, when I used to teach the workshop that we had here for factorial designs, the single most common, I would say the most common question I got is, I have no idea what sigma I should use. I have no idea what quote unquote my process noise is. Now, of course, if you open up a textbook that was written by a statistician, they're going to say use historical or SPC data. Use and make an educated guess. Now, I've been around, you know, I've done this long enough to know that these suggestions are often useless, especially when somebody's working in a new process. Okay, they have just no idea what the noise is in the process. So here are 2 strategies that I can, you know, that you can use as to kind of get around this. So first of all, here's one. What you can do is you can start with an unreplicated factorial design. So like in our cake example, we could just do a single replicate of a 2 to the 3 design. We can fit a main effects model. We can get the estimate of sigma from the ANOVA, because once you fit the model, it's going to give you an estimate of the noise. And then what you can do is you can simply add additional runs using this more accurate sigma that you have now until you get a power that's high enough. So it's like a 2-stage process. First, you do, you know, kind of a very small experiment. You get the sigma from it. And then what you do is you can, okay, just simply use our design augment feature and add runs until you get a power that's sufficiently high. Okay. Another strategy that I've seen people use, that I've kind of come up with, but I've never seen published anywhere, is if you're doing center points, do a few center points first. Okay, so run maybe 3 to 4 center points. Compute the standard deviation of those runs. Of course, in theory, those responses should be exactly the same, but that basically never happens. The standard deviation of those runs is the pure error. Okay, multiply that by 2 to get a rough calculation of the total error, and then use that sigma to build a factorial design around the center points. So you can still keep the center points you did. You just might do a second block of runs with maybe 1 more center point and then do the factorial runs there. And that's probably going to give you, you know, you could probably get a rough, you know, a very decent estimate of sigma just here. That's probably going to be better than fully guessing, but these are the things that I like to suggest. And then finally, before we move on to the RSM section here, sometimes I get people that still say, you know, even after I give them these suggestions, they still don't know what to do, or they still have no idea as to what delta or sigma they should be plugging in. These are kind of quote unquote the rules of the street that I came up with over the years. These are not perfect by any means, but this is mostly, I think it's still much better than doing absolutely nothing. If you have absolutely no idea about your process, plug in delta 3 and sigma 1 if you're just looking to detect huge obvious effects. So this is a signal to noise ratio of 3 to 1, which is equal to 3, which is which is very large. So if you're just looking to detect very large obvious effects, just plug in 3 to 1 and see what power you get. If you're looking to detect moderate to fairly large effects, plug in delta 2 and a sigma of 1 and just see what type of power just see the ballpark where you're at. Again, I don't love these suggestions, but I still would much rather at least take a look at this rather than just do nothing. Finally, you could plug in delta of 1.5 sigma 1 if you're looking to detect small to moderate effects. You can go below 1 if you want to detect real small effects. However, the law of diminishing returns does start to kick in right around the signal to noise ratio of like 1.3 to 1.5, which is going to result in an explosion of runs, and each additional run that you add is going to increase the power by a smaller and smaller amount. So if you have absolutely no idea what to do, just think, do I want to find small, medium, or huge effects, and plug in one of these, and just to at least, so you, as a sanity check, so you at least see kind of roughly where you are at. Okay, so that, and then somebody asks here, can I use design augmentation to increase the power of a design or not? And absolutely you can. I'll just go ahead and point you in the right direction. You can go back to the spreadsheet here. You can click augment design and augment with, you could replicate the design here, or you can use, so for example, if I wanted to add a second replicate, I can use replicate design, or unfortunately, we don't have time to talk about it here, but you can also use any number of these augmentation methods here. Some of them are optimal, some of them are things like semi-fold or center points, but yes, the answer is absolutely, and in fact, sometimes we recommend starting with a smaller design to get kind of a lay of the land, and then augmenting, don't blow all of your budget in a single pass, and then not have any runs after that. So, okay, that takes us through the factorial section here. So let me just make sure I'm in the right spot here. All right, so we've got about 15 minutes left, and we're going to talk about evaluating response surface designs. Okay, so here's kind of the setup here for those of you that maybe used older versions of our software. Here's kind of a legacy, that neon yellow design space we used to show. Factorial designs usually only look at the highs and lows of each factor, possibly at the center points as well. However, designs, DOEs that consider 3 or more levels of each factor are typically referred to as response surface designs. Okay. The goal of response surface designs is not necessarily to detect what is significant and what's not significant. In other words, detecting active effects. But really what we're looking for is to fit a precise model, also known as a response surface, to the data. Okay. This response surface, what's nice is you can use it for optimization to figure out where should you expect the maximum or the minimum. You could also use it for making predictions at locations where you didn't collect any data, so interpolating, or maybe even, it's a little risky, but even attempting to extrapolate. So therefore, design evaluation for response surface designs will be different than for factorial design. So power is all about detecting what's active. We don't necessarily care that much about that in response surface experiments, so power is not the best metric to use when evaluating a response surface design. And now here I have to make a note, because we are limited on time, we don't have time to go into mixture designs. However, response surface and mixture design evaluation is very, very similar. Both of them use the fraction of design space plot. Okay, so we're only going to consider the RSM case here. So how can we evaluate an RSM, a response surface design, before performing the experiment? So first of all, again, is it fully randomized? Well, if you build it in our software, you shouldn't really have any issues. Is the design capable of mathematically fitting the model that we are interested in? Is aliasing an issue? Do we care about any terms that are aliased? Will the model have good precision? And do we think blocking is necessary? Now, the one we're going to focus on is this, will the model have good precision? Okay. And we will go through the design evaluation tools now in our software. Okay, so once again, I'm just going to take a simple example here just so I can illustrate some of these tools. So once again, We will work through an example to show how we would evaluate an RSM design before actually doing the experiment. So this is a chemical reaction. This is available in our tutorial data. So we have three factors. We have time that goes from 40 to 50. We have temperature that goes from 80 to 90. And we have catalyst that goes from 2 to 3. And the response of interest is the yield of the reaction. So the design, for those of you that are familiar with it, it was set up as a central composite design with, I believe it was 20 runs. So a central composite design looks like something like this. You have your factorial here in the middle, but then you also have some star or axial points here. You have some of them here. And then you're also doing some runs here at the center. So this is going to allow you to fit more than just a factorial model. It'll allow you to fit a quadratic model. Here's what the design looked like here. Okay, they did this over 2 blocks. Okay. The reason why is because they started with a factorial design and then later turned it into an RSM design, and they did it on separate days. So they blocked by the day to protect against any day-to-day variation that might have occurred. Maybe the temperature of the lab, maybe it was a different operator, maybe who knows what else it could have been. Okay. So this is what it looks like. Okay, the big question is this design sufficient? So the most important things to check is aliasing and the fraction of the design space plot, which talks about precision. Aliasing means the following. It means that you could estimate your desired model cleanly. Okay. In a response surface experiment, we usually want to fit at least a quadratic model. Why? Because that allows us to fit curvature. It allows us to see where's the minimum, where's the maximum, and so on. So we want an experimental design that's capable of fitting a quadratic model without aliasing or confounding the quadratic terms with linear terms. So as an example, if you want to fit a straight line, you need at least 2 unique points. If you want to fit a squared polynomial model, you need at least 3 unique points. This is what we're talking about. We want to make sure that the design has at least enough unique levels and enough runs that you could even mathematically fit that model. So if I go to our software, I can go to the evaluation here, and I can, let me open this. This is a tutorial data, and I'm just going to go to the analyzed version here. Just to save a, whoops, I don't want to save that. Tutorial data, chemical conversion, and no, I don't want to save this. All right, so I can go to the evaluation, and I can go to the results here, and I could look at the aliasing here. Nothing is aliased in the quadratic model, so I'm good. Now, if I wanted to use this central composite design to try to fit like a cubic model, I probably see that that this isn't going to work. Why? Because I have like 6 or 7 more terms in the model than I do runs, so I can't even mathematically make that fit. Okay. And if you click on alias matrix, you'll see that, for example, if you look at your ANOVA and you see factor A on the ANOVA table, it's not actually factor A. It's factor A plus sum of A cubed. What you see as A squared B is actually sum of A squared B plus B squared C minus B cubed. So you're not actually able to estimate, like, for example, the linear and the cubic effects independently of one another. So if I was interested in a cubic model, I would have to create the experimental design with that in mind, with enough runs to support a cubic model. Okay, so this is just basically the same thing that I had shown. But a central composite design, they were interested in fitting the quadratic model. They didn't think that cubic behavior was really an issue. And oftentimes going beyond a quadratic model is not necessary. Even if your process is fairly complex, a lot of times a quadratic model will be good enough to find the minimum or maximum. Okay, even if you don't quite get the behavior modeled of your system modeled perfectly. So finally, the last thing is we need to check, this is the fraction of design space plot. So this is a little, sometimes confuses people. I'm going to try to, in 5 minutes, give you a crash course on how you would use this. So we need to check whether this design is large enough or if it's too large. once again, detection of active effects is not the primary goal of response surface experiments. So instead, what we want is we want to fit a model to the data that has high precision and that's accurate. So we use a new tool. We're not using power, we're using the fraction of design space plot here. Now, a lot of people have a really hard time of kind of intuitively understanding the fraction of design space plot. So here's the question I always like to ask. So I think everybody here has probably seen a political poll. I mean, we get them every 2 years, we're bombarded with them. And you might see something like 46% of respondents said they prefer candidate A, but there's always this with a ±3 margin of error. So the question is what is this margin of error and why are they reporting it? Well, the margin of error comes from the fact in this case is that you're not asking every single voter for their opinion. If you poll 100 people today, 46% might prefer candidate A, but if tomorrow you go out and poll another 100 people that you choose randomly, you might get 44%, and then the next day you might get 49%, and so on. So you're not getting, the 46% is an estimate of what the real value is. Okay, there's just natural variability, and it's the same thing that happens when you do an experiment. If you do an experiment and you fit a model and you maximize, and then the next day you do the same exact experiment, you fit a model and you maximize, you're not going to get the exact same maximum at the exact same location. I mean, they're going to be pretty close to one another, but they're not going to be exactly the same. Okay. Also, if you use a model to interpolate, you're not going to get a prediction that's right on the model. So if I have a model that looks something like this, and I have, it goes through my data that looks like this, if I want to predict this location here, I mean, the model predicts that it's right here on this line, but chances are if I go and I do this experiment, the actual data I collect is not going to be right on that line. So the same issue here with natural variability crops up in response surface experiments. So we fit a model to the data, and what we can do, and what we want to do is we want it to predict the response at new locations, possibly interpolate a minimum or a maximum. So notice here, if you go to Design Expert plots, you'll see that most of them have these green bands, green or red bands around them. And what these are called confidence intervals. And a confidence interval tells you that, well, okay, the model is this black curve here, and it's predicting at what's going on at this factor here. However, it's not a perfect model. There's some uncertainty with it. It wasn't fit perfectly. There's noise, there's random error. And that's what this interval is telling you. The interval is essentially telling you, giving you kind of a plausible range of future values. So notice the green intervals, as I said, these are called confidence intervals, and they tell us how precise the model predictions are. If the confidence intervals are very, very tiny, then I could probably be pretty confident that my model is going to be pretty stable. That means that my predictions should probably be, pretty close. If I go and I try to do a new run here, if my confidence intervals here are narrow, I should probably expect the next run to be pretty close to the model versus here where they're pretty wide. Okay, so loosely speaking, we want, before we do the experiment, we want to have a chance of generating a model that has, good prediction properties and has very tight confidence intervals. So the question is can we get the confidence intervals around the predictions to be narrow? And the answer is yes, we can, but like with power, the more precision you want, you require more data, more runs, or less noise in the process. So this fraction of design space is basically the analog of power in the factorial case. So to compute the precision of a design, we need two key ingredients. We need the half width, and we need the noise in the process. So to get the half width, this is a question, this is the margin of error. This is what I always like to ask people that I'm working with. Let's say you're preparing to do the experiment, and let's say you think about this kind of in the future. If you optimize your process, let's say maybe you maximize it. What is the plus or minus uncertainty that you'd be okay with around that optimum point that you might find? So Like with this yield, let's say that you're just as a thought experiment, let's say the maximum yield might come out to be 70%. What if you look at the confidence interval around it in the point prediction and it says, okay, I'm expected to get a 70% maximum yield here, plus or minus 30%. That means 40 to 100% is like an interval of plausible values. I mean, how confident would you be? The answer is probably not really. But the question is what level of confidence what level of precision are you okay with? Are you okay with a plus or minus 10%, plus or minus 5%, maybe plus or minus 1%? That plus or minus is the half width that you need to come up with. The noise, the sigma, is exactly the same as it is in the factorial case. And what we want to do is we want the design to produce confidence intervals of plus or minus h, and at least some people say 95%, some people will say 80%, some people will say 99%. I like to do roughly 90 to 95%. So we want to make sure that we have our desired level of precision in at least 90% of the design space. We might not get it close to the edges where we don't have a ton of data, but we at least want the center of the design space to be capable of having as much precision as we'd like. So now what I'm going to do is I'm going to demo the fraction of design space. I'm going to go to graph. It's in the graphs section here. And you use this little widget here. So I think the delta that they were interested in for the chemical reaction was 4% and a sigma of 1%. So delta of 4, sigma of 1. And you look here for this FDS statistic here. Okay, I think I have my legends set to just a little bit too much information, but what you want to look for is this FDS. This is 1. This means in 100% of the design space, my model will predict, the confidence interval around my model predictions will be plus or minus 4% or lower. If it turns out that I really wanted a lot more precision, like a delta of 2 to sigma of 1, okay, the FDS is still 99%. So in 99% of the region, my confidence intervals will be at most 2%. I'll have that margin of error and at most in 99% of the space. And if I had like a delta of 1.5, well now, okay, the FDS falls to 85%. And you get the picture. So basically, if I want a higher level of precision, if I want 100% FDS here with a delta here of 1.5, a half width of 1.5, probably going to need to add more runs. And then once again, this is that street smarts thing. A lot of times people still have trouble kind of conceptualizing this and figuring out exactly what they're able to live with. I'm not going to go through this, but this is analogous to that factorial case where if you're looking to protect against massive issues, plug in 3 to 1. If you're looking for moderately precise models, plug in 2 to 1. If you're looking for fairly precise models, 1 to, I would say 1.5 is probably going to be okay, but the closer you get to 1, once again, you're going to start getting into the law of diminishing returns there. So let's just wrap this up. We have, I do apologize for going a little bit over time, but here are some take-home points. Just a summary here. Always evaluate a design before performing the experiment, even if it's just literally looking at each run and in your head mentally kind of figuring out, is this run valid? Could something go wrong? And so on. If you're using a factorial design, aim for 80% power in the main effect. If you're using an RSM or mixture design, aim for 90 to 95% in the FDS plot. Go through each run in the spreadsheet and perform it mentally. Make sure it's not going to give you useless data or cause an explosion or something like that. Like if you have temperature and pressure set to its high value, make sure there isn't something that you know is going to go wrong there. Because unfortunately, the software doesn't know or care about your specific process. It just cares about the math. And when in doubt, you don't use your entire run budget in a single pass of the experiment. If you're able to run a small pilot or calibration experiment or exploratory experiment, do that, get some information, and then add runs using that information. And here are just some resources for you if you found this interesting. Of course, we have a bunch of free and paid resources. So if you really found this interesting, consider taking one of our workshops where we take this 45-minute crash course and we expand it out into a much longer time period with software tutorials. We always encourage people to go to our YouTube channel. We have a lot of videos, a lot of free videos covering a wide variety of topics, our tutorials and help system. As I mentioned, we have our live hands-on workshops, and all of this stuff can be found at our website, www.staties.com. So learning about design evaluation, the final take-home point, it doesn't take that long of a time. I mean, you could become pretty competent with it in an hour or two, and you know what? It's going to serve you for every single experiment that you do for the rest of your career. So I think the ROI is massive, and that's why we encourage it very, very heavily here. So I want to thank everybody here. I know we went a little bit over time. I do want to thank, I mean, pretty much everybody that joined stuck around until the end. So if you want to reach out to me personally, you can contact me here. This is my personal email. But if you do have any more statistical focused questions, please use that stathelp@staties email, because that'll go to a larger group of people that might be able to answer faster than I can on my own. So we want to wish everybody the best of luck. Thank you for coming, and we hope that you found this useful and it'll help you down the road. So thank you very much, and take care, everybody.